Something vast and largely invisible is shaping the future of one of the most dangerous fault systems on Earth, and it is not where most people have been looking. Beneath the seafloor west of Vancouver Island, far below the rolling Pacific, processes are unfolding that do not fit neatly into the long-standing assumptions about how great earthquakes begin. If strain builds silently for centuries, what else is building with it? If the fault is locked, what is quietly moving within it? And if pressure is rising, what exactly is holding it back? The Cascadia Subduction Zone stretches for roughly 1,000 kilometers, about 620 miles, from northern California to southern British Columbia. It marks the boundary where the oceanic Juan de Fuca plate is forced beneath the North American plate. This boundary is capable of producing earthquakes exceeding magnitude 9, events that arrive without warning and reshape coastlines within minutes. The last full rupture, in the year 1700, sent a trans-Pacific tsunami to Japan and left behind a geological record of sudden land-level change along the Pacific Northwest. For decades, the dominant understanding has been deceptively simple. The plates lock together. Stress accumulates. The upper plate bends upward slightly as energy is stored. Then, in a single catastrophic release, the fault slips, the land drops, and the ocean surges inland. But emerging observations from offshore and beneath Vancouver Island suggest that this model is incomplete, not wrong, but missing a critical ingredient. That ingredient is fluid. Deep beneath the seafloor, water is not just present, it is active, mobile, and pressurized. It is carried downward with the subducting plate, trapped in minerals, sediments, and fractured rock. As pressure and temperature increase, that water is released, migrating upward into the overlying crust. It does not simply disperse. It accumulates, channels, and sometimes becomes trapped in zones where it can fundamentally alter the behavior of the fault itself. Recent geophysical imaging has revealed that these fluids are not evenly distributed. Instead, they form complex networks, reservoirs, and pathways that extend through the crust above the megathrust. These networks can be mapped indirectly using electrical resistivity, because fluids conduct electricity more easily than solid rock. The resulting three-dimensional images show zones of elevated fluid content beneath parts of Cascadia, including regions offshore of Vancouver Island. What emerges from these images is a system that behaves less like a simple locked interface and more like a layered, evolving structure where pressure, permeability, and stress interact continuously. Fluids accumulate in certain regions, particularly where geological formations act as barriers. One such barrier is a thickened section of crust that limits how fluids move upward, causing them to pool and build pressure over time. This matters because fluids at high pressure can weaken faults. When fluid pressure increases, it effectively reduces the friction holding the plates together. In some cases, this can promote slow, silent slip, movements that release energy gradually rather than catastrophically. Cascadia is known for these events, often referred to as episodic tremor and slip, which occur roughly every 14 months beneath parts of the region. These slow slips do not generate large earthquakes, but they do transfer stress along the fault, redistributing where energy is concentrated. Yet the presence of fluids introduces a paradox. In some areas, they appear to facilitate these slow releases of energy, acting almost like a pressure valve. In others, they may do the opposite, helping to lock the fault more tightly by altering the mechanical properties of the surrounding rock or by concentrating stress in specific zones. Nowhere is this tension more significant than near the northern Cascadia margin, offshore of Vancouver Island. Here, long-term measurements of fluid pressure from boreholes drilled into the seafloor have provided rare, direct insight into what is happening below. These instruments, positioned roughly 20 kilometers, about 12 miles, landward of the deformation front, record changes in pressure that reflect deformation within the crust. The data suggests that fluid pressure is not static. It fluctuates, responding to both slow slip events and longer-term tectonic processes. At the same time, geological records along the coast indicate that uplift is occurring, albeit slowly. Terraces and ancient shoreline features show that parts of the land have risen over thousands of years at rates of roughly 0.4 millimeters per year, about 0.016 inches annually. This uplift is consistent with the gradual bending of the overriding plate as stress accumulates. But the key detail lies in how much of that deformation becomes permanent. Only a fraction of the strains stored between earthquakes is released elastically. Some of it is retained in the structure of the crust itself, altering the geometry of the fault zone over time. This means that each seismic cycle does not simply reset the system, it modifies it. The presence of fluids adds another layer of complexity, influencing how and where that permanent deformation occurs. Offshore discoveries have added further urgency to this evolving picture. In one location along Cascadia, a seafloor seep known as Pythias oasis has been observed venting fluid that is several degrees warmer than the surrounding seawater. The fluid is chemically distinct, indicating that it originates from deep within the subduction system rather than from shallow sediments. Its temperature, approximately 9 degrees Celsius above background, or about 16 degrees Fahrenheit, suggests that it has traveled from significant depth before emerging at the seafloor. Such focused venting implies that fluid pathways are not only present, but actively transporting material upward. These pathways can act as conduits that relieve pressure locally, but they also indicate that pressure is being generated at depth in the first place. The question is how widespread these conditions are beneath Vancouver Island. Seismic and electromagnetic surveys suggest that fluid-rich zones may extend across large portions of the northern Cascadia forearc. These zones are not uniform. Some areas appear highly saturated, while others remain comparatively dry. The boundaries between these regions may be critical in determining how the next rupture unfolds. If a rupture begins in a fluid-rich zone where pressure has reduced friction, it may propagate differently than one that initiates in a more rigid, locked segment. It could accelerate more quickly, or it could stall. It might transfer stress into adjacent areas, potentially triggering a cascade of failure along the fault. There is also the question of segmentation. Cascadia does not necessarily rupture as a single continuous event every time. Geological evidence suggests that some past earthquakes have involved partial ruptures, affecting only certain segments of the fault. The distribution of fluids may play a role in defining these segments, acting as invisible boundaries that either promote or inhibit the spread of rupture. Meanwhile, the record of past megathrust earthquakes continues to grow. Deep-sea sediment studies have identified multiple events over the past 7,500 years, preserved as layers of disturbed sediment on the ocean floor. These records confirm that Cascadia has produced repeated large earthquakes, though the timing and extent of each event vary. This variability is precisely what makes the current findings so significant. If fluids are influencing the mechanical behavior of the fault, then changes in their distribution or pressure could alter the conditions leading up to a rupture. Unlike the slow accumulation of tectonic stress, fluid movement can occur over shorter timescales. It can respond to subtle shifts in pressure, temperature, or permeability, potentially changing the state of the fault in ways that are not immediately visible at the surface. Beneath Vancouver Island, this hidden system is still being mapped. Each new dataset, whether from seafloor sensors, boreholes, or geophysical imaging, adds another layer of detail. Together, they are revealing a fault zone that is dynamic, interconnected, and influenced by factors that extend far beyond simple plate motion. The implications are not yet fully understood, but the direction is becoming clearer. The next Cascadia rupture will not occur in a static environment. It will occur within a system where fluids, pressure, and rock interact in complex and evolving ways. And as those interactions continue to unfold beneath the ocean floor, the conditions that will shape that future rupture are already taking form. The subducting plate does not descend as a uniform slab. It carries with it a thick blanket of oceanic sediments, altered basalt, and hydrated minerals that have interacted with seawater over millions of years. As this material is driven downward, increasing temperature and pressure trigger a sequence of chemical reactions. Minerals that once held water within their crystal structures begin to break down, releasing that water into the surrounding rock. This process, known as dehydration, occurs progressively with depth, and its effects are cumulative. The released fluids do not simply vanish into the surrounding matrix. They accumulate along zones of weakness, migrating upward through fractures, faults, and porous layers. In some cases, they become trapped beneath impermeable formations, forming overpressured pockets that can persist for extended periods. In others, they find pathways that allow them to rise toward the seafloor, feeding vents and seeps that mark their presence far above. The significance of these processes lies in how they interact with stress. Within the Cascadia system, stress is not distributed evenly. It concentrates along the megathrust interface, where the two plates remain locked over large areas. This locked zone is where the majority of strain accumulates between major earthquakes. However, the presence of fluids can alter both the strength and the behavior of this interface. Where fluid pressure is high, the effective normal stress acting across the fault is reduced. This can make it easier for the fault to slip, even under lower levels of shear stress. In such regions, slow slip events are more likely to occur, releasing energy gradually and producing the low-frequency tremor signals that have been detected beneath much of Cascadia. Yet these same conditions can also contribute to instability. If fluid pressure increases to a critical level, it can weaken the fault to the point where a rupture can initiate more easily. The transition from slow slip to rapid failure is not fully understood, but it is thought to involve a combination of factors, including the rate at which stress is applied, the properties of the surrounding rock, and the distribution of fluids within the fault zone. The northern portion of Cascadia, particularly offshore of Vancouver Island, exhibits characteristics that make this transition especially complex. Geophysical surveys have identified regions where the crust above the subducting plate is unusually thick and mechanically distinct. These regions can act as barriers to fluid migration, causing pressure to build beneath them. At the same time, they may influence how stress is transferred along the fault. This creates a layered system in which different sections of the fault behave in different ways. Some segments appear to be strongly locked, accumulating stress over centuries. Others are more prone to slow slip, releasing energy in smaller increments. The boundaries between these segments are not fixed. They can shift over time as conditions within the fault zone change, particularly as fluids move and pressure evolves. Evidence for this shifting behavior comes from a combination of seismic monitoring, geodetic measurements, and offshore instrumentation. Slow slip events beneath Vancouver Island have been observed to migrate along the fault over periods of days to weeks, sometimes spanning distances of several hundred kilometers, roughly 180 to 310 miles. These migrations indicate that the fault is not failing uniformly, but rather in a sequence of localized movements that propagate through the system. At the same time, the accumulation of strain in the locked zone continues. Measurements of ground deformation using satellite-based positioning systems show that the coastline is being compressed and uplifted as the plates remain coupled. This deformation is subtle on a human timescale, but significant over decades and centuries. It reflects the ongoing storage of energy that will eventually be released in a future earthquake. What is becoming increasingly clear is that the distribution of fluids may influence where this energy is stored and how it is ultimately released. In areas where fluids are abundant and pressure is high, the fault may slip more easily, reducing the amount of stress that can accumulate. In contrast, regions with lower fluid pressure may remain more strongly locked, allowing stress to build to higher levels. This contrast can create sharp gradients in stress along the fault, potentially acting as triggers or barriers for rupture propagation. One of the more striking implications of this is the possibility that fluid-rich zones could act as gateways for rupture initiation. If a rupture begins in such a zone, it may encounter less resistance initially, allowing it to accelerate. As it propagates into more strongly locked regions, the behavior of the rupture could change, potentially increasing in intensity as it releases the accumulated stress in those segments. Alternatively, the transition between zones could slow or even halt the rupture, leading to a partial event rather than a full margin earthquake. This variability is reflected in the geological record. Studies of coastal subsidence and uplift, combined with offshore sediment analysis, indicate that past Cascadia earthquakes have not all been identical. Some appear to have involved the full length of the fault, while others were more limited in extent. The intervals between these events also vary, ranging from a few centuries to over 1,000 years. This irregularity suggests that the system is influenced by factors beyond simple plate convergence, with fluid dynamics emerging as a key candidate. Further insight comes from the study of seismic velocities within the crust and upper mantle. Regions with high fluid content tend to exhibit lower seismic velocities, as the presence of fluids affects how seismic waves travel through the material. Mapping these variations provides another way to infer the distribution of fluids beneath the surface. In the northern Cascadia region, these velocity anomalies align with areas identified through electrical resistivity as being fluid-rich. This convergence of evidence strengthens the case that fluids are a pervasive and influential component of the system. At the same time, the interaction between fluids and rock is not static. As fluids move, they can alter the properties of the surrounding material, changing its strength, permeability, and response to stress. Over time, this can lead to the development of new pathways or the sealing of existing ones, further modifying the behavior of the fault. This dynamic evolution means that the conditions leading up to the next major rupture are not fixed. They are being shaped continuously by processes occurring deep beneath the surface, many of which are only indirectly observable. The challenge lies in integrating these observations into a coherent understanding of how the system will behave in the future. Traditional models of megathrust earthquakes often assume relatively uniform conditions along the fault, with variations in behavior attributed primarily to differences in stress accumulation. The emerging picture from Cascadia suggests a more complex reality, in which fluid pressure, rock properties, and structural features interact to create a heterogeneous and evolving environment. This has implications not only for understanding the timing of future earthquakes, but also for anticipating their characteristics. The magnitude of a rupture, the extent of fault slip, and the resulting ground shaking and tsunami generation are all influenced by how the rupture propagates along the fault. If fluid distribution affects this propagation, then it becomes a critical factor in assessing potential hazards. Offshore monitoring efforts continue to expand, with new instruments being deployed to measure pressure, temperature, and deformation directly on the seafloor. These measurements provide valuable data on the state of the system, capturing changes that would otherwise go undetected. At the same time, advances in computational modeling are allowing researchers to simulate the complex interactions between fluids and fault mechanics. These models incorporate data from multiple sources, including seismic imaging, laboratory experiments, and field observations, to explore how different conditions might influence the behavior of the fault. While uncertainties remain, the direction of the findings is consistent. The Cascadia Subduction Zone is not governed solely by the slow convergence of tectonic plates. It is also shaped by the movement and pressure of fluids within the Earth's crust, particularly beneath regions such as Vancouver Island, where conditions favor their accumulation and retention. As these fluids continue to migrate, accumulate, and interact with the surrounding rock, they are contributing to the evolving state of the fault. They influence where stress is concentrated, how it is released, and how rupture may propagate when the system eventually reaches a critical threshold. The next Cascadia earthquake will emerge from this complex environment, carrying the imprint of processes that have been unfolding for centuries beneath the ocean floor.